Let us take a brief recap of what we have learned so far. We have looked at thermodynamics, we have looked at the laws of thermodynamics, mainly the first and the second law, and the third law was actually about the lower bound or lower limit of entropy of a given system. And we have looked at various implications of the laws on different systems and how do we calculate these thermodynamic parameters, equilibrium parameters. And then we have started talking about statistical mechanics to understand the internal structure of a system so as to get these equilibrium parameters. And first we have done the microcanonical ensemble, and then we have introduced the canonical ensemble, and we are presently doing the canonical ensemble. So, for today the topics that we are going to cover is a general discussion about the distribution, and what I mean by the distribution is this PR is equal to exponential minus beta E r divided by sum over r e to the power minus beta E r, and also the partition function which is written as sum over r e to the power minus beta E r. And this I have emphasized that this calculation of the partition function for a given system holds the key to a number of thermodynamic parameters which we are eventually interested in. So, we will have to calculate this partition function, which means we have to calculate this sum, and how to calculate this sum and in a closed form particularly, that is something that we are going to discuss. Okay. We will also talk about the energy fluctuations in the canonical ensemble, and this is going to reveal a very important thing, that why statistical mechanics works so well for large number of particles or large number of systems under consideration. We will talk about the entropy in this canonical sense, and then we will do a number of examples of the canonical ensemble or other applications of this ensemble and get various physical quantities or measurable quantities. So, to begin with, let us discuss more on the distribution, the canonical distribution, which is called as the Boltzmann weight, or what we have discussed as what is the probability that our system occupies an energy level E r, and which is given by exponential minus beta E r divided by sum over r exponential minus beta E r. Beta is nothing but 1 over k T, that is the inverse temperature. Okay. So, this we have written as 1 over z e to the power minus beta E r, where z denotes the partition function, and here we will call it a canonical partition function, because we are doing a canonical ensemble, which means that our system is in contact with a heat bath, and eventually the system comes to an equilibrium temperature T, which is the same temperature of the bath and the system, and the system is not allowed to exchange particles with the bath, but only energy, such that it comes to an equilibrium temperature. Okay. So, this the limiting case, if we take if E is a continuous variable, which means that even if the energy levels are discontinuous, we assume that they are too close to each other and can be considered as a continuous variable, then we can write this distribution P E d E. Now, we are not using this E r, because we are using E as a variable, a continuous variable, and we want to ask this question: what is the probability for we find our system between E and E plus d E, which is given by P E d E, and this is proportional to the distribution, which is minus beta E and it's multiplied by the density of states. Now, this is being introduced for the first time. Let me tell you what is density of states. So, G E is called as the density of states, or in short we will call it as a DOS. So, first if we convert a sum into an integral, a discrete sum into an integral, we should always in the integrand we should always include this density of states, because this density of states may actually vary depending on energy. As you see that it is written as G of E is written as it is a function of E. Okay. And so this PEDE, that is the probability of finding the system between E and E plus DE, is given by this Boltzmann weight, which is so this is the Boltzmann weight or Boltzmann factor, let us call it as, and this is density of states. Okay. And how do we calculate density of states, say for a given simple system, and let us do that, which we will need anyway for later use. We are considering that we have a K space. So, we go to the K space representation where it is easier to visualize. So, if you have in a K space, we know that if we move a distance 2 pi over L, we get 1 K point. So, which means that the K points are separated by 2 pi over L, where L is some length of the system. Okay. So, if we move unit distance, then we get a L over 2 pi K points. Okay. If you move a distance dk, that is you want to find out how many K points are there between K and K plus dk, then we will get L over 2 pi into dk number of K points, and this is the density of states which we call as Gk dk. Okay. And we will convert it into GEDE by using the dispersion for a given system. Now, this is in 1D. If you think that you want to calculate the number of states between a sphere of radius k and k plus dk, so you want to calculate the number of points here, okay, k points here. So, we will multiply it by instead of this dk, we will multiply it by 4 pi k square dk, and then this becomes a volume. So, this number of k points is equal to L over 2 pi whole cube, because now we are in 3D and we have to multiply it by k square dk. Okay. So, this is simply equal to V over 2 pi whole cube and 4 pi k square dk. So, this we call it as Gk dk. Okay. And then we will simply use the dispersion relation which is dependent on a given problem. So, let us come to this from here, let us go here and let us see that suppose we take a non-relativistic dispersion, parabolic dispersion, then E equal to h cross square k square by 2 m, and we can calculate. So, k square is equal to 2 m E by h cross square. So, we get a k square here, and now we have to get a dk. So, this is a 2 k dk is equal to 2 m by h cross square dE. So, dk is equal to this 2 will cancel, and we get a 2 m not 2 m, just m by h cross square, and a dE divided by a k, and k is nothing but root over 2 m e by h cross. So, dk is equal to m by h cross square dE divided by root over 2 m e and by h cross. So, h cross will go up and 1 h cross will cancel, and now we got a k square as well as dk. So, we can write this down here G E d E for this 3-dimensional non-relativistic dispersion as V over 2 pi whole cube 4 pi k square is 2 m E by h cross square, and then it is m over h cross and 1 over root over 2 m e, and there is a d e there as well. So, this is a d e. Okay. So, this root over 2 m e makes it root over 2 m e here. So, this actually goes as, apart from all these constant factor, it goes as e to the power half. So, it depends on energy. In certain cases, it may not depend upon energy, but that is besides the point. In most of the cases, it depends on energy, and in this particular simple case, we have shown that it depends on the energy as a square root of E. In fact, in 3D it is square root of E, in 2D it is a constant, and in 1D for this parabolic dispersion it is 1 by root over of E, which means e to the power minus half. We will see some of them as we go along. Alright, so this is the density of states. So, once again we write this thing which we have started with. So, P E d E in a continuum notation, we should not we can write it as equal to with some constant, but let us just continue with this exponential minus beta E g of E and d E. Okay. Now, notice one thing, this one is actually a decreasing function of E. And this one is a monotonic function. It is usually it could be a growing function. In this, at least in this particular case, the e to the power half, it is like a growing function. It is like a function that grows like this. So, let us just write it as a growing function. It could be a constant as well. Or at least it's nevertheless, it's basically a smooth function or a well behaved function. Okay. It may have divergences in certain conditions or in certain situations, but let us not talk about that at this moment. So, what we can do is that if this is like a convolution of two functions, as you can see, exponential minus beta e is one function and g of e is another function. So, one of them is decreasing monotonically going down and the other is monotonically going up. There must be some energy for which this the derivative of this function or this function has an extremum value. Okay. So, what I mean to say is that for some E, let us call it as E star, say this P E must be having an extremum. Okay. So, what I mean by that is, so if you have that to be true, then we have this exponential minus beta e g of e, this at e equal to E star, this is equal to 0. That is what the extremum means, that you take a derivative and this derivative vanishes at that particular value. So, let us try to take this derivative. It's the two functions, so use the chain rule. So, we will have a g of e minus beta into e to the power minus beta e plus e to the power minus beta e d g e d e and the whole thing at E equal to E star has to vanish. Okay. So, if we divide the entire expression by e to the power minus beta E g of E, that is the basically the P E, which cannot be equal to 0. So, this G E goes away and the exponential minus beta goes away, and then we get a minus beta and a plus 1 over G of E dg dE, and this whole thing at E equal to E star is equal to 0. So, divide by. All right. So, this is simple. We are just trying to get at some inference from here, and this tells you that if we perform this or rather simplify this, just take the beta to the other side, and then what we get is that del del E of log of G of E at evaluated at E equal to some E star, which minimizes this function, is equal to beta, and recognize that S is equal to k log G of E. Okay. Since we have written it as a log of the number of microstates, and these microstates should scale as the density of states, that is the number of states that are there in some interval E and E plus D, but still let me write it as just a sort of relation that it goes as this, and hence this log of G can be replaced by in the top line can be replaced by S, and we get a del S del E at E star E equal to E star, and let us call this E star to be equal to some U, some energy. This is at T, which is nothing but equal to k b beta. Okay. So, that tells you that this distribution, or rather this the definition of temperature actually occurs, or rather this distribution has an extremum at a given value of E, which is E star, and if you really recognize that this is the definition of temperature or thermodynamic temperature, which is T is equal to inverse of del S del E, where E actually, or here the E star represents the internal energy of the system, and this U actually correspond to the average energy. So, this is a U is the average energy which we have calculated it, which is that this E of R, and this we have calculated, and this we have called as U, or you can divide it by the number of particles and call this as say small u and so on, which is energy per particle or in the internal energy per particle. So, this is the average energy, U is the average energy, and E star is the most probable energy. Now, this is an important result. It tells you that the average energy becomes equal to the most probable energy, which also tells you that the distribution is very sharp. The distribution is peaked at the average energy, sharply peaked at the average energy, or which is also the most probable energy. Okay. And this tells you that this canonical ensemble or canonical distribution is not too different than microcanonical. Now, this is a quite an important statement. It also justifies that why we are shifting from one distribution to another distribution, one ensemble to another ensemble, and there is nothing so very different about all these ensembles. In a microcanonical ensemble, you wanted to calculate the number of microstates at an energy E, or at best between an energy E and E plus D, where D is much smaller than E, which means that almost in a very thin shell of energy you wanted to calculate the number of microstates, and from the number of microstates you wanted to calculate the entropy and various other things. In the canonical distribution, you say that let us relax this condition, that because energy is anyway not a measurable quantity. So, let us say that the energy is being exchanged between the system and the surroundings or the heat bath or other members of the ensemble, and hence come to an equilibrium. But however, that gives you a distribution which is very sharply peaked, and where the most probable value for energy of that distribution is same as the average value. And how we make that statement is through this expression or through this equation, which tells you that you get a 1 over T as the definition from del S del E, and that occurs at E equal to E star, which we know as the average energy. So, E equal to E star equal to U is where we get a proper thermodynamic definition of temperature, and hence the distribution must be very sharply peaked, so that we would not make so much of mistake if we still consider microcanonical ensemble and say that the energy of the system is really confined in a thin shell, which is what we have done earlier. Let us just see one more small point here, which will tell you that indeed the two distributions are same, and even when we go to grand canonical, things do not change much. So, let us expand ln of P e, okay. P is the canonical distribution about this value, that is about E equal to E star, which is nothing but equal to U. Okay. So, if you do that expansion, so log of P e which is equal to log of e to the power minus beta e multiplied by the density of states, and this we do the expansion. The expansion will give you a beta u plus s over k. This is the first term. So, we do a Taylor expansion of this, and the Taylor expansion, just to remind you, that it is equal to f of x naught plus del f del x at x equal to x naught into x minus x naught. So, the first term is f of x naught, which is written here, and we have replaced E star by u, and plus half of del 2 del E 2, and the first term is absent because of the reason that this is an equilibrium distribution. So, the first term goes to 0, and the only non-zero term that is there is del 2 f del x 2 x equal to x 0 x minus x 0 square. Okay. And we have shown that earlier, that the first derivative vanishes because it gives you an extremum condition. So, the first non-zero term is the second term, which is here, and this is equal to log of e to the power minus beta e g of e, and this is evaluated at e equal to u and e minus u square. Okay. So, multiplied by that. Okay. So, it will be here. Now, this as you see that it is like a constant, let us call it as some say 1 over alpha, and why we write 1 over alpha would be clear soon. This is a constant as well. okay, and there is some constant and then it is multiplied by E minus u square. So, this distribution actually looks like a Gaussian distribution. So, log of P e is equal to some constant value which is minus beta u minus T s, just that taking the beta out. So, the k goes away from there and you get a T s here, and a minus 1 over alpha, and you have a E minus u whole square, and then of course, there are terms which we have neglected. Okay. So, this tells you that the P of E, which is nothing but this e to the power minus beta E g of E, and this is equal to e to the power minus beta u minus T s and e to the power minus alpha E minus u whole square. Okay. Let me write with a square bracket here. Okay. So, this is the distribution, this is a constant, this is a Gaussian. Okay. This exponential minus alpha x square, and this is what was claimed, that this is like a bell shaped distribution with the mean is at u. So, it is the mean is of course at u, as you can see that it is like a term which is like exponential minus alpha x minus x 0 square. So, this has a mean at e equal to or e equal to u, or which means x equal to x 0, and the width of the distribution, what I mean by width is that it is called full width at half maximum, or the second moment is at 1 over alpha, where alpha is constant which you can calculate by calculating this double derivative of this distribution, log of the distribution. All right. So, this reconfirms that the distribution that we are dealing with in the canonical ensemble or the canonical distribution is indeed a sharply peaked distribution, which has the most probable value is equal to the average value, and it is peaked about the average value, and it has a width which is like 1 over alpha here, which can be obtained from this calculating the double derivative of the log of the probability. Okay. So, let us do one more thing. The whole purpose of doing this is to convince that the statistical mechanics we learn a number of ensembles, but they really do not give you results which are significantly different than each other. And we should be happy about that, because if you take a representation or if you take an ensemble or if you take a distribution which produces completely different results, then that does not serve any purpose. Then we have to revisit that what our assumptions are, because for the thermodynamic quantities which are the final goals of our of these doing statistical mechanics, they cannot vary. So, we should in the limiting case we should get all these distributions to give us same result or something very similar. Okay. Let us do the fluctuations in energy, and this is going to teach us again something important. So, fluctuations in energy means the energy this of our system, which is E r, and this the average value of E r, etcetera. These are there are fluctuations because there are statistical fluctuations and in these measurements, and these statistical fluctuations are important to calculate, and the final result that we get tells you that in the thermodynamic limit, that is as the number of copies or number of members of the ensemble, they go to infinity, these fluctuations die out, which tells you that the statistical mechanics that we do, or the statistical description that we undertake for a given problem makes sense, and it's correct. So, what we mean by fluctuations, a priori it means that we are trying to calculate this quantity, and which is nothing but E r square average minus E r average square. Okay. You might see that some books actually write it as E r square average with a bar and E r bar. We may have also done that, but they mean the same thing, that putting a bar and putting a sort of angular bracket, they mean the same thing. We are just trying to calculate the statistical average. Let us see what that comes out. So, if we have to calculate this as a fluctuation, so fluctuations in energy means we have to calculate these quantity delta E r, okay, or the square of that, does not matter. So, so we have to individually calculate E r average and E r square average and so on and so forth. So, we have already calculated this. This is E r exponential minus beta E r and sum over r exponential minus beta E r. Okay. This is a general definition for any thermodynamic average or any statistical average, or average of any statistical quantity that we want to calculate. So, E r is the energy of our system, you weight it by the Boltzmann factor and divided by the total probability, or this is the partition function. And you see how you get a E r here, you can simply get it by taking a derivative with respect to beta. So, if you take a derivative of this quantity, so del beta of e to the power minus beta E r, and this will give you a minus E r e to the power minus beta E r. Okay. And then you absorb the minus sign, say you put a minus here, then you get a plus here, and so on and so forth. So, this is a trick that is widely used there in order to write these averages in a sort of closed and nicer form. So, this can be written as a minus del beta of log of z, okay, and this is nothing but equal to u, that is the internal energy. And you see that z is equal to e to the power minus beta E r sum over r. If you take a log of that, log of z is equal to sum over r minus log of this e to the power minus beta E r, and now you take a del beta of log z, you get exactly what you there, because the log will make it go down. So, there will be a term which is exponential minus beta E r, and then there will be a sum here, this one is not required, and there will be a sum here which will have a E r exponential minus beta E r, and that is what you exactly want. So, learn this well, so that this is the average energy, and which we call as the internal energy of the system. Okay. So, U is the internal energy. All right. So, now how do we calculate this quantity, which is E r minus E r square, and then the square of that, the square should come outside, yes, here. Okay. So, this is nothing but equal to E r square minus E r square, E r average square. So, this is equal to delta E r square. And so, we have to calculate each one of them, as I have said earlier. So, we already have calculated the last one, that is ER average, which is here. We just have to calculate ER square, and it is not difficult to see that if you have to get 2 powers of ER, that is 2 factors of ER, you have to do a double derivative of this log z with respect to beta. So, this is nothing but equal to ER square minus ER average square is equal to 1 by z. This is just writing it completely, I mean the expression I am sort of from the first principles, and minus 1 over z, there is sum over r ER e to the power minus beta ER whole square. Okay. So, this is the first term, that is ER square average, and this is ER average, and then you take a square of that. All right. So, now let us look at an identity which is del beta of 1 over z del beta. If you look at that, then it becomes equal to 1 by z, keep the first term constant and differentiate the second one, and this is 1 over z square del z del beta square, okay. And that is exactly what you have. So, this is equal to the first term is this term is this term, and this is this term. So, your ER delta ER square, which is this quantity, let us write it with a bracket, this is delta ER square, okay. This is equal to del beta of 1 by z del beta, okay. I hope this is clear. We have just look at this expression that is written in the middle, and then del r square is equal to del ER square equal to del beta of 1 by z del beta. Now, I have to take a derivative. So, we have again 2 terms inside the square bracket, 1 over z and del z del beta, and we can do it simply by doing a del beta of log z, and this is nothing but minus del beta of ER average. That is what we said, del beta of log z is a minus of del beta, I mean minus del beta log z is equal to ER average. So, this delta ER square is minus del beta of ER, okay. And ER is nothing but we know that it is U, that is the internal energy, and this is del U del beta, and what we can do is that we can calculate this as a minus del U del T and del T del beta, and beta equal to 1 over k T. So, del beta del T is equal to minus 1 over k T square. So, you have del beta del T. So, this can be inverted as just minus k T square, the minus sign goes away, and we get is it as k T square del U del T, and this is nothing but n k T square, and the specific heat del U del T specific heat, there is no rhyme or reason that we should consider it as at a constant volume, but let me still write it as C V just to sort of make sure that this is the specific heat. It even if it is not at constant volume, we can still write it as simply C. So, you could go ahead and write it as C. Just for concreteness, I will write it as C V, and so this is equal to N k t square, because this del u del t gives you a n CV. So, you have a k t square and CV, and so that tells you that this quantity delta E r square is equal to some proportional to some t square, and it is the scale is set by the specific heat. So, if we want to calculate the mean fluctuation or the relative fluctuation, then what we do is that we calculate this E r square average minus E r average square divided by this half and by this E r, and this is nothing but root over of n k t square C v and divided by n u. I am writing it specifically by introducing or rather this writing this internal energy as an extensive quantity. So, u is equal to n into small u, so capital N into small u. Okay. So, that is how you do it, and if you look at this, this has a 1 by root over of n. So, which means as n tends to infinity, the delta E r by E r. So, this quantity delta E r by E r average, that goes to 0. Okay. So, which means that the fluctuations vanish, and that is how the statistical mechanics works so well. It gives you accurate results or close to the correct result because the fluctuations vanish in the limit of large n. Okay. And there is another small point here which you may find it useful in some context, that is now this delta E r square is greater than 0 for sure. I mean, all these quantities are positive, and this delta E r square rather, because it is a square of the fluctuation, this has to be necessarily greater than 0. And if you go back, then you will see that this is like del 2 del beta 2 log of z that is greater than 0. So, this this proportional to this del 2 del beta 2 log of z. Now, that tells that the log of z is actually has a positive curvature. In the beta space. So, in the inverse temperature space, this log of z has a positive curvature, because del 2 del beta 2 is talks about a curvature of a system. All right. So, this establishes an important point, that this is really statistical mechanics works so nicely because the number of particles or the number of ensembles is very large, and you take an average over all these ensembles. To sort of bring an analogy with again with your the students and marks and so on and so forth, if there is a class that consists of a small number of students, the statistical analysis will lead to erroneous results. Which means that if you have very small students, the notion of the standard deviation or the variance etc., will not be very well defined, whereas this is much more well defined when you have a very large distribution and you get a bell shaped or a Gaussian curve in the distribution of marks. So, how do we extend this discussion? We are continuously talking about this this PR, which is the distribution, the canonical distribution, and getting various information out of it. And let us do that or rather continue doing that, and let us calculate what is the entropy. And entropy is nothing but minus k T log z, which is what we have derived earlier. So, this is minus 1 over beta log z, and this is equal to minus 1 over beta log of summation over r exponential minus beta E r, and this is nothing but equal to minus 1 over beta log z. Okay. So, this is a simple expression we can calculate. If we know the partition function, we can calculate this free energy, Helmholtz free energy, and the entropy is obtained as minus del F del T at a constant number of particles and volume, and this will tell us that this is equal to nothing but k and a beta square. There is a little bit of algebra that I do, please convince yourself that this is correct, and this is equal to k log z and k beta over z and sum over r E r exponential minus beta E r. So, that is the expression for entropy. And again using the distribution. So, this is nothing but 1 over z e to the power minus beta E r. So, that tells you that a z p r is equal to exponential minus beta E r. Okay. So, this is one thing. So, if you want to know, let us just see this one more time. This del f del beta that you see here, it is equal to minus 1 over beta square log z minus 1 by beta z del z del beta, and now you can get this expression that you see there. Okay. So, this is z p r equal to exponential minus beta E r. So, minus beta E r that is equal to log of z p r. So, minus beta E r is this quantity, and so S is equal to, which is k log z, the first term there, and the second term can be written as k over z sum over r, and this is minus log of z p r e to the power minus beta E r and so on. Okay. And so, this is simple to find, and this is k log z minus sum over r k by z log z into z p r and minus k r p r log p r. P r is given here. So, this is your P r, okay. And this z will cancel, and we have this quantity. So, this the first two quantities cancel in the following sense, that there is a k log z and a sum over r P r, and there is a k sum over r P r log of P r. Now, this sum over P r is equal to 1. So, there is a k log z minus k log z, they cancel, and we get entropy to be equal to minus k P r summation over r P r log P r. This is an important quantity. So, we get the entropy directly from the distribution. So, it is minus k summation over r P r, let me write it neatly, P r log of P r. Okay. It is a useful quantity, and we will use it in order to calculate the entropy directly from the distribution. Now, this also help us to reaffirm our understanding that both the microcanonical and the canonical would give us same result. And in microcanonical distribution, we have a PR to be equal to a constant, which is what we have said, and let us call this constant as some 1 over omega, where omega denotes the number of accessible states, the number of microstates, so to say. Okay. So, S gives you minus k and sum over will just sum over omega now, and it is 1 over omega because PR is 1 over omega, and there is a log of PR which is 1 over omega. Okay. This quantity is log of 1 over omega is equal to log 1 minus log omega. Log 1 is 0. So, this is just simply minus log of omega. So, the minus sign is goes away, and we have a minus k sum over omega 1 over omega and minus log of omega. So, this minus sign becomes a plus sign. Okay. So, this is the expression for entropy, and this is inside the sum, but then every term is a constant. So, if you sum over omega, you simply multiply it by omega, that is number of accessible states that you are summing up on. So, this is k 1 over omega log of omega into omega. So, this sum is replaced by this omega because there are omega number of terms, and they cancel is equal to k log omega, and something that we have saw earlier. So, this is the entropy which is k log number of microstates, and then we have derived it from the canonical distribution as well. So, whose expression is S equal to minus k PR log PR, where PR is a distribution which is 1 over z exponential minus beta ER. Let us do one example that we have already done, so that this understanding will be complete there. So, this example is this n non-interacting spin half particles in a magnetic field. So, the energy of the system is written as minus mu 0 h, and there are n of them. So, let us call this a sigma j. Well, I mean sigma j can take values plus 1 or minus 1, j equal to 1 to n, and we are directly writing the energy, but you can write down the Hamiltonian of a system whose energy would be given by this things, because now everything is like a quantity that we know. So, for all these j equal to 1 to n. Okay. So, sigma j takes these discrete values, that is it is a plus 1 or minus 1, so again in the microcanonical ensemble we have taken n such spins, and we have assumed that n1 are pointing up, n2 are pointing down, and we have written down the energy, total energy and the total number of particles, and have calculated the number of microstates by simply taking a n factorial divided by n1 factorial and n2 factorial, which gives the number of the total number of microstates present with out of n particles, n1 have the possibility of n1 are pointing in the up direction, which means has a value plus 1, and n2 are pointing in the downward direction having a value minus 1. Now, we will use canonical ensemble to solve the problem. Okay. So, the canonical partition function, now this is very important because we have not said yet that how to calculate that sum. So, this is the sum that we need to calculate, and look at this, that we will simply write it as sigma j and exponential minus beta, and then we will write it as mu 0 h and sigma j. There is a j equal to 1 to n, and so it looks a little complicated to begin with, because so there is a plus sign, because you have a minus sign here and a minus sign here. So, this should be plus. Okay. All right. So, let me write it a little more familiar fashion, because you are seeing sum in the exponent as well, let's and which is true, which would be there. I just write it as exponential beta mu naught h sum over j equal to 1 to n sigma j. There is a double sum there. One sum is outside, which tells us that we should sum over two possibilities of sigma j. Either it takes a value plus 1 and minus 1, and we add both the possibilities. So, this sum is to take into account the sigma j equal to plus minus 1. However, when you see inside the bracket, there is another sum, and this sum actually have sigma j, and now we have to sum over all the spins, taking this value sigma equal to sigma j equal to plus 1 or minus 1 for each j. So, there is a tentativeness whether we can calculate this both the sums in a closed form, and it turns out that it actually is very easy to do it. If you write this as now, you can make this ornamental things, that this is actually a function of n and v, and it is at a given temperature T. So, you can write it as n, v and T. I am simply writing it as z at this moment. So, this is equal to so a bracket, and I am doing it for the first spin, and I will write it as exponential beta mu 0 h. So, this magnetic field is h, in a magnetic field h. So, beta mu 0 h, this is 1, the second term will be a sigma 2, that is a second spin. Again I will write exponential beta mu 0 h, and I will write down this, and for all the spins, and this is for sigma n exponential beta mu 0 h. So, I see that this double sum really factorizes and makes life easy. And is easy to calculate. Okay. How do we calculate this? Before that, let me write then this z is equal to, rather z is equal to each one of the terms. So, let me write it as z 1 n to the power n, because there are multiplication of such n terms. So, I only have to calculate z 1, that is one of the square brackets, and I will be fine, because I just raise it to the power n, because all these terms give us identical results. Okay. And z 1, that is any one of them, is sigma equal to plus minus 1, and we have an exponential beta mu 0 h sigma. Okay. So, each one of the terms look like this, and this is like exponential beta mu 0 h plus exponential minus beta mu 0 h. You see, sigma equal to plus 1 gives you this term, and sigma equal to minus 1 gives you this term, and this is nothing but 2 cosine hyperbolic beta mu 0 h. Okay. And this cosine hyperbolic is a function that you may not have come across so frequently, but they are there in a large number of places in physics. in the particularly in statistical mechanics. And let me also write this sine hyperbolic x, which is exponential x minus exponential minus x by 2, and we also write which will need tan hyperbolic x, which is exponential x minus divided by exponential x plus exponential minus x, basically nothing but sine hyperbolic x and cos hyperbolic divided by cos hyperbolic x. So, we get a nice and closed form for this, and then calculating the total partition function becomes easy. So, this z is equal to z1 to the power n, which is 2 to the power n, and cos hyperbolic beta mu 0 h whole to the power n. Okay. But really it is not this n we do not have to worry about, because as soon as we are going to take a log of z in order to calculate f, the Helmholtz free energy, the n comes out as a prefactor, and then we can talk about free energy per particle, say small f, and be done with this capital N. So, f is equal to let us call it f is equal to or rather which is minus k t log z, and from there we calculate a f which is f over n, which is a minus k t log of cos hyperbolic. Let me make this apparent, the temperature dependence, by replacing mu by 1 over k t. So, that is the free energy per particle, and similarly entropy per particle. You can keep the capital N also, there is no problem, but it is just that it is sort of carrying that n over and over again does not make sense. So, we just talk about per particle. Per particle means here what we mean is that per spin. So, this is equal to small s, okay, which is s over n. This is equal to a del f del t at a given h with a minus sign. I should not miss the minus sign, because this is an important quantity. So, this if you calculate s, you just have to you have a log of this cos hyperbolic, and the t is there in the denominator of the argument of cosine hyperbolic, but it is not difficult to do it. You can just practice it and get it. So, it is 2 cosine hyperbolic mu 0 h by k t. One term comes from the log of this, and then the other term is the mu 0 h by k t tan hyperbolic mu 0 h by k t. So, that is the entropy per particle, and the magnetization, the other important quantity in this context, is the magnetization per particle. Which is given by m equal to minus del f, this has to be a small f, del h. Let me make sure that I have written a small f there, yes. I will come back in a moment with this entropy one more time, but at this moment it is the calculation of the magnetization at a given temperature, which just do it carefully, you will get it as mu 0 tan hyperbolic mu 0 h by k t, and this result is identical as the microcanonical result. If you go a few lectures back and see that the result for this spins by calculating this n factorial divided by n 1 factorial and n 2 factorial, take the log of that, use Stirling's formula and get the entropy and then get the magnetization, it is exactly the same, which means that this really looks like it goes through 0. Okay. So, this is like the mu 0 h and this is the minus mu 0 h. So, this m as a function of we will write it as mu 0 h by k t and so on. Okay. Now, we have some more discussion here, especially with the entropy, and this will be done in a while, and we want to discuss what is called as negative temperature, and which we will do later. But let me sort of calculate another quantity which is measured in experiment called as the magnetic susceptibility. And magnetic susceptibility is written as a TH, and this is really a del m del H at a given temperature and in the limit H tending to 0. So, for very small fields. So, this is equal to mu 0 square H. So, I take this this expression of m and then take a derivative with respect to H. It is inside the tan hyperbolic. So, first you take a derivative of tan hyperbolic and then what is there inside. So, this gives you a sec hyperbolic square, and so this is k t, and this is a sec hyperbolic square mu 0 h by k t. Sec hyperbolic square is nothing but 1 by cos hyperbolic square. So, you have seen cos hyperbolic as cos hyperbolic x as e to the power x plus e to the power minus x by 2. So, you may want to explore that what happens at small x or large x, in the sense that truly this result is valid for large temperature, because we are talking about classical systems. So, if we talk about very low temperature, we may get wrong results. In fact, it gives you wrong results as we can just see it here. So, at H equal to 0, we can get this as this chi goes as H tending to 0, rather H tending to 0, chi of T H tending to 0 gives you this mu 0 square H by k t, and this is a famous formula called as the Curie's formula, where the paramagnetic susceptibility at a large temperature goes as 1 over T. And as I said, that this is really important to understand that this mu h by k t is small here, is much smaller than 1, and in this limit this is true. And that tells you that we actually need to either the cos hyperbolic or the sec hyperbolic we need to expand, and say I will just give you this hint that cos hyperbolic for small x you can expand it and you get 1 plus x plus 1 minus x divided by 2. So, this becomes equal to 1. So, the sec hyperbolic also becomes equal to 1, and that is how you get this prefactor out, and which looks like 1 over T. Now, chi of T, let us just write without that H going to 0, is like 1 over T, which is called as the Curie's law. Okay. So, once again we make this comment that valid for large temperature. Okay. Now, two important things. One is that that we have made a one-to-one correspondence with the microcanonical ensemble and calculated the magnetization, which looks exactly same. and then we have calculated the susceptibility. We recovered Curie's law, which it should, which is valid for n independent spins in a magnetic field, and the large temperature behavior of that of the susceptibility goes as 1 over T. So, we will stop here and continue with more discussions on this, and it is very important to make a comment on negative temperature, which we shall do in the following class. Thank you.